Problem number 4, very interesting problem, I would say very important problem too. I have a very long wire, we think of it as infinitely long, with the charge per unit length, which I call lambda, 3 times 10 to the minus 10 coulomb per meter. Here is this long wire, here is x equals 0, and I'm asking you a question which is not asked by your teachers, but I want to do that first, and then you'll see that the rest comes out very easily. And that question is, what is the electric field at a location D anywhere away from the wire? Well, the way we can do that is in 2 ways. Either we do it in a nasty way, which is the way that chapter 22 is dealing with, or we do it in a beautiful, easy way, which is chapter 23, which is Gauss's law. And I will do both. I feel obligated to do the nasty way because after all, the problem has a number 22. The nasty way. Here I select at location x a small element dx, which therefore contains a charge dq, which is lambda times dx. This little charge element alone will produce at this location an electric field in this direction, which I will call dE. It is a vector. And I can decompose that into this direction, the y direction, so this would be dE y, and I can decompose that into this direction, which would be dE x. And we have an angle theta here, and we have an angle theta there. And this distance from this point to this charge, I will call that little r, equals the square root of d squared plus x squared. All right then. Now, first the nasty way. I first want you to appreciate that calculating dE is very easy. The magnitude of dE, now only the magnitude, equals 3 times 10 to the minus 10 times 9 times 10 to the 9 times dx divided by that distance r squared. And when you put in the numbers, you'll find 2.7 divided by r squared times dx. That's the magnitude. Now clearly, if you add up all these elements here, there cannot be any net vector in the direction, in the x direction. They will all cancel out. So the only one that survives is this one. So I don't even bother about the x direction. So I only calculate dE in the y direction. That of course is this value times the sine of theta, and I find then 2.7 d divided by r cubed times dx. And so if I now want to know what the total value for Ey is, I have to execute the integral from x all the way from minus infinity to plus infinity of dx divided by r cubed, and I will write down for r cubed d squared plus x squared to the power 3/2. And to be frank with you, I'm not very good at integrals. I find this a very nasty integral. I looked it up and I did even better. I asked my graduate student to confirm it. And if you do this integral correctly, and I'm sure you are better at it than I am, then it is 2 divided by d squared. And so the net result is that Ey then becomes 5.4 divided by d. And if Ey has to be 0.5 newtons per coulomb, that will be the case if the distance to the wire is 2.8 meters. So far, the nasty solution. Now, the beautiful solution, Gauss's law, which you will learn in chapter 23. Suppose I have here a closed surface. It is essential that it is closed. Cannot be an opening. And at the surface here, I have small surface elements, and I erect small vectors, all perpendicular to the local surface. A ds here and a ds here. And by convention, they are always pointing outwards from inside the surface to outside the surface. And there could be an electric field vector here, due to the charge that is inside here. There could be an electric field here, and there could be an electric field here. What Gauss's law now tells me is that the closed surface integral over this entire surface of E dot ds, it is a dot product, equals the total charge inside this volume divided by epsilon 0. And I can only use Gauss's law in a meaningful way if I can create a geometry which is easy. And the easy geometries always require symmetry, and you can only get symmetry with spheres, with cylinders, and with planes. And we'll do one of each. And this is going to be the cylinder. So, here is my infinitely long wire, and I am going to introduce what I call a Gaussian surface. It must be a closed surface, and think of it as being a coin, which could have any width that you want to. So this would be a cross-section of the coin. The thickness of the coin is unimportant, I'll call it L, and this now is distance d from the wire. If I try to make it look a little bit three-dimensionally, which is always a little difficult, then it would look like this. So this is the coin. It's actually a little cylinder, but it's completely closed. I hope you realize that. It's a closed surface. Now, the E field right here at the ends must be pointing outwards for reasons of symmetry. There cannot be any component like this or that. Nature cannot decide between left and right. And so the E field here must also be pointing outwards, radially outwards. The same here, but also on any surface element here, it must be pointing radially outwards. In other words, if I looked at this surface from this side, and if this were that surface, which then had a radius d, then everywhere at the surface the E field must be pointing radially outwards for reasons of symmetry. How about the values of ds? Well, ds per definition is pointing outwards, so ds here is also pointing outwards, ds here is pointing outwards. So everywhere where we have here these E vectors, the ds and the e's are in the same direction. So the dot product can be ignored because the cosine between the angle between E and ds is 1. So let us calculate the electric flux that goes out from this curved surface. That should be very easy. That is the surface area itself, which is 2 pi times d. It has here a thickness L, so this is now the total volume. Not volume, this is the total surface area of this curved surface. I multiply that by E according to Gauss's law. I have to add now the flux that escapes from the sides, and that then equals 3 times 10 to the minus 10. That is the charge that is located here at the wire, which has a length L times L divided by epsilon 0. What is the flux that escapes from the sides? The flux that escapes from the sides is 0, because ds It's always perpendicular to the surface and is therefore in this entire problem for this side and for this side of the coin, the ds dot E is 0 because E and ds are perpendicular to each other. So there is nothing here. It is 0. And so you'll find immediately what the E vector is and what do you see? The L of course cancels because nature couldn't care less how wide you take this cylinder, and if you work this out you will see that you find exactly the same result as you had before. But the beauty, think of the beauty. No nasty integrals, just a choice, and that's very important, the choice of one nicely symmetric geometric surface. Must be symmetric, otherwise you're nowhere. And you apply Gauss's law, you don't even have to think, you have to be careful that you take the dot product into account. Very often can you set it up in such a way that the dot product is only non-zero through certain surfaces, in this case through the curved one, and that it is 0 through other surfaces, in this case the flat ones. And then you execute the recipe, you don't even think anymore, and the E field pops out. Gauss' law is fantastic. It cannot always be used if there is no symmetry. It's always correct though, but you can use it to your advantage if you choose the right surfaces and put in the right symmetry. And of course the charge distributions also have to be symmetric, otherwise it's pretty hopeless.